Hi, welcome to the third session on group theory. We shall continue. In the last session, we defined in a monoid an element, what is meant by an element to be invertible. So we will continue that. So today I start the streaming. Yes, yes, okay. So let G be a monoid. What does it mean? There is a binary operation which is associative and which has an identity element which may denote by 1 or E. Okay, right. So I say A in G is a unit or invertible if there exists a B in G such that AB is identity which is also BA. So that means A and B both commute and their product or binary operation is E. Okay, right. I use the word unit because, as I said, in ring theory, okay, with respect to multiplication, this identity will be called 1 and this invertible element will be called a unit. That's why I'm using. But if you are not comfortable, you just assume this is invertible. Okay, Invertible, invertible. Okay. So we want to study the properties of a thing. Okay, invertible elements. So let us do that. Let G be a monoid. Let 1 in G be the identity. We had already seen, okay, it's unique. Okay, the first thing is if A is, yeah, if A is invertible, there is a unique B such that AB equal to BA equal to identity. That means the inverse is unique. I think I proved it in the last lecture, in the last session, but let me again go through a proof. So notice that suppose there are two elements B and C in G so that AB equal to E equal to BA and AC equal to C identity, okay, equal to CA, right? Then let's look at this product ABC. Notice that this is well defined. Given any one A to generalize associative law says there is a unique element which is A1 to AN, therefore this means. But this with respect to that, this also equal to ABC, right? Oh, sorry, not ABC. I want to consider BAC, right? Okay. Thus, I can group it as B into AC using associative law. But what is this? AC is 1, therefore it's B times 1 and hence it's equal to B. But this I can also group as BA times C, right? But what is BA? That is 1 times C, that is equal to C, right? Therefore we get B equal to C, right? Notice that associativity is very important for this. It's crucial, okay, for this proof. Okay, right. The second thing we want to prove is if A is a unit, so is A inverse. But that is obvious because A inverse. Okay, I'm sorry. Again, I'm jumping ahead. Okay, so the unique inverse, if A is a unit, the unique inverse of A is denoted by A inverse. It's just a notation. Okay, this is just a notation. Okay, now the second part I want to say is A in G is invertible or unit. So is A inverse. That is the the unique inverse of A. That is clear because A inverse is identity, because A inverse is the inverse of A, but and hence this, right. But this says A. Let us look at A inverse. A times A inverse identity, and A inverse times A is identity. Therefore, this says that A is the inverse. It is it's an inverse, but inverse are unique. Therefore, it is the inverse of A inverse. So, what is that you get? So, notationally, we get A inverse. Inverse is A. Okay. Pause. Review. Proceed. The third thing is, suppose A and B in the monoid are invertible. So you see that easier for me to write units. Then so is AB. That is, remember, AB is an element of G. There is no dot. Okay, don't get mistake with that. Okay, the unique okay, the product of two elements under the binary operation be denoted by AB, that is an element of G, then it is also invertible. So how do you think I will prove it? You may remember your formula, but don't, let's not worry about it. Okay. So suppose C in G is the inverse of AB. Okay. Assume the result true. Okay. Then there exists one inverse of this element AB. Call it C. And it's unique, right? Then what should I have? What should I have? I should have AB times C must be 1. Right? So now since A is invertible, I can multiply, okay, I can look at this element A inverse with AB and C. Do you understand this? This is an element I am multiplying by A inverse. Okay. I have to multiply both sides with the same thing, therefore it is A inverse times 1. Is that clear? But what is this? This is A inverse. Right? But this, using associativity, we know how, and general law, it is A inverse A, B, C. Now I can group A inverse B together. But what is that? That is 1 times BC. Therefore, what I get is BC is A inverse. Do you understand this? Now, what do you think I will do? Right? Now, multiply both sides by B inverse. Let us look at B inverse BC. Okay. Where will it go to? It will go to B inverse BC. Okay. But that will go to, because BC is A. This is same as B inverse A inverse. That will go to B inverse A inverse. But where? What is this? This is going to be C. Right? Therefore, I get C equal to B inverse A inverse. Right? If you don't like this, simply do that. I have A, B, C is identity. Yeah, apply A inverse both sides. A inverse A, B, C equal to A inverse 1. That is A inverse. But group them together. Therefore, B is equal to A inverse, and multiply by B inverse. That is B inverse A inverse. But this is 1 times C. B inverse A inverse. So I found out my C is B inverse A inverse. Typically, the textbook will say do this AB into B inverse A inverse. Okay, by associativity is A into B inverse A inverse. But this is A into 1 into A inverse. That is A into A inverse, which is identity. Similarly, B inverse A inverse into AB. So this is verification. Okay. Somebody told you this is the inverse and you checked it is the inverse. But here we found out the inverse. We found out the expression for the inverse. Do you understand the difference? Pause, review, proceed. Okay. Then the fourth one is By induction, I can do that. Suppose A1, A2, An in G are all units. They are all units, meaning it's invertible. Okay. Then let me look at A equal to A1, A2, the product of all these elements. Then I want to say A is invertible. A is a unit. And what is in A inverse? That is the question. Right? Okay. So we already know when n equal to 2, then we know A1, A2. This is invertible, its inverse is A2 inverse, A1 inverse. Right? Therefore, by induction, suppose I have A1, A2, A3. What will you think I will do? I want to find its inverse. What do you think I will do? I will do A1, A2 into A3. Right? Right? Now, what is the inverse of this? Therefore, that's inverse is the inverse of this. This inverse of this is A3 inverse into A1, A2 inverse. But by we already know this is A3 inverse, A2 inverse, A1 inverse. Do you understand this? Okay. So we want to generalize. So let us assume for n greater than or equal to 3, we have shown that A1, A2, An inverse is An inverse, An minus 1 inverse, A2 inverse and A1 inverse. Assume this. This is the induction hypothesis. Right? Now suppose you give me n plus 1 units. Then I want to know A1, An plus 1 inverse. Okay? Equal to what? But remember, I can write this. This is A1 to An into An plus 1 inverse. Notice that this is some element, this is another element in the group. For n equal to 2 case I can use. Therefore, this by definition is An plus 1 inverse, not by definition, by what you proved for AB inverse is B inverse A inverse. This I am calling as B perhaps. This is my A. You understand? Okay. This is An plus 1 inverse into A1 An inverse. Is that okay? But then I know what this is, An plus 1 inverse, and by induction hypothesis this An inverse, An minus 1 inverse, A2 inverse and A1 inverse. So we proved the result. So what did we prove? We proved that if A1, A2, An are units, that inverse is An inverse, An minus 1 inverse, A2 inverse, A1 inverse. Now let's do the fifth one. The fifth one is, suppose A is a unit. Right? Now let me take A1 equal to A2 equal to An equal to A. Right? Then call this B equal to A1 to An. This by definition An. Right? This is how we define A to the power n. You understand that? So we know that A to the power n is a unit by 4 because the product of n units. And what is its inverse? Therefore, A to the power n inverse by definition is, look at A1, A2, An, there is An inverse, An minus 2 inverse, A2 inverse and A1 inverse, but they are all A. A inverse, A inverse, A inverse, A inverse. This is what? This is A inverse to the power n. Okay, this is n times. Right? So what you have shown is, if A is a unit and for every natural number n greater than or equal to 1, including z plus, remember by assumption A to the power 0 is 1, which is a unit. Okay. Did I prove that? Maybe I didn't prove. I will do that in a minute. Okay. Then A to the power n is a unit and its inverse is, look at the inverse of A1, A, look at the inverse of A and raise it to the power n. Okay, and notice that the identity element is a unit, because 1 times 1 is 1 equal to 1 times 1, right? Therefore 1 is a unit. It's a trivial, but I should observe as the zeroth. Okay, if this is the fifth, this must be the zeroth. Okay, pause, review, proceed. Now let's go to the next one. Now remember, given any element in a monoid, okay, any element in a semi group, what is a semi group? Binary operation and associativity, right? Then we define what is meant by a to the power n by induction. Do you remember? And perhaps with a make it a monoid. Even the last time I made the same mistake, and with identity, right? And a to the power 0 is 1, and we know what is a squared, which is a times a. Assuming a to the power n is defined, a to the power n plus 1 is a times a to the power n. Okay, right. So we have defined this. Remember, this is true only for natural n in z plus. Now what we want to do is, if G is a monoid with identity equal to 1, and if A is a unit, then for any integer n we want to define. Is the question clear? Right. So law of exponents, in any monoid, for any element we define if n is a non-negative integer. Now if G is a monoid, A is a unit, then I want to say I can define a to the power n for any integer, right? So for natural numbers or non-negative integers we have defined. How do you think I will define for negative integers? Let us look at, when n equal to minus 1, I want to say a to the power minus 1, right? I want to say a raised to the power n, where n is now minus 1. What is the natural way? Okay, a to the power minus 1, but it is the inverse of a, which is anyway denoted by a to the power minus 1. Do you understand the difference? The subtle difference, understand. Without knowing this law of indices, we already denoted by A inverse, the unique inverse B. Okay, if A is the unit, B is the unique inverse, then a to the power minus 1 is B. That is what you are saying. But unfortunately, we already introduced the notation a to the power minus 1. Okay, please appreciate this. We will come to that. So, when n equal to minus 1, then if B is the unique inverse of A, then a to the power minus 1 is B. But this is a notation now, that is a to the power, let me say a to the power n is my B. But n happens to be a to the power minus 1. You understand? But earlier itself we started using this notation. I should have avoided perhaps earlier, but usually one doesn't. Is that point clear? Don't get confused. Think about it. I want to define a to the power n when n is minus 1. It has to be the unique inverse. But unfortunately, the unique inverse we started denoting by a to the power minus 1 already. Okay, good. Now, how do you think I will define for any n? So, suppose n is negative, then let's look at minus n. Yeah. So, that will be positive, right? It's a natural number. Therefore, a to the power minus n is defined. Right? So, I want to define, if n is negative, a n is a minus n inverse. But remember, this is same as a. I don't want to confuse, just let's go slow. Do you understand this? I want to define this. A inverse, this is defined because now n is a positive number, right? Natural number. Therefore, this is defined. And we have seen this, since A is a unit, okay, A inverse as a unit, Therefore, this one makes sense. Okay, a to the power minus n is by definition a to the power minus 1, a to the power minus 1. But what is that object? That object is a power n inverse. Yeah, let's go back to what I said. We will define a to the power n for n. A is a unit. Okay, n is a natural number. Okay, then we define a to the power n. We found out this is nothing other than a inverse to the power n. Do you understand? Yeah. So I want to define a. If n is negative, maybe I will start with a number so that there won't be any problem. Let us say a is. I want to define this. Okay. When n equal to minus 1, I already defined it is a inverse. Right. Therefore, what will I do? This I will define to be to cut a to the power minus 1 and take it to the power 5. Does this make sense? Yeah. But this we also know by earlier thing it is a to the power 5 minus 1. Yeah. Therefore, we define if n is negative, then a to the power n equal to maybe I will write here n positive so that there won't be any confusion. A to the power minus n by definition is a inverse to the power n or a inverse a to the power n inverse. Okay, I stuck to n negative, that's why it might cause problem, but let us understand this. Okay, let's go back. So if n is negative, okay, I want to define a to the power n. So let us assume a to the power n is positive, then I want to define a to the power minus n. This is the definition symbol. The left side is defined by the right side. Now since a is a unit, a inverse exists and raising to the power n exists. So this makes sense. Is that clear? That is my definition. But we also know from the earlier by 5, but this object is nothing other than a to the power n. Look at the group element a times a times a, where n is positive. You understand? Therefore this makes sense. And we know it is invertible. Take its inverse. Okay. Pause. Review. Proceed. See, because of high school algebra, okay, you always learn to manipulate symbols. Okay, even when it comes to group theory, etc., just like that people do, you think it's all right because you got used to it. But now you see the difference. We have to make a definition and make sure it is sensible. You follow that? So these are the things, please don't find it just because you find it difficult, don't skip it. Okay, again revise it if necessary, watch it again. Okay, rewind, watch it, or rewind, watch it with your friend and discuss. Okay. Make sure this kind of basic conceptual understanding is there, then you will see most of mathematics becomes easier for you, not by simply manipulating symbols, because algebra has become manipulation of symbols for most of the students. Okay, right, let's go. So what should be the next thing now? What should I think I should? Next should be what? Now you remember, if A is a unit, is a monoid, a unit, then we define a to the power n for every integer n. Right? Now remember, for any element, and n is a non-negative natural number, we define a to the power n, and then we did law of exponents. Right? So we want to prove law of exponents. Let us now prove or extend the law of exponents to negative indices. Right? So let us start with that. of exponents. So G is a monoid. A in G is invertible or a unit. Okay. N is an integer in Z. And similarly A, B and M, N are integers. The first thing we want to say is a to the power m times a to the power n is a to the power m plus n. Right. This is okay. If m, n both positive, both in Z plus, okay, already known. Let me just check. Yeah, right. Okay. So now assume that we are looking at m and n in n, but I am looking at a to the power minus m into a to the power minus n. So we want to check whether it is a to the power minus m plus n. This is what we want to check. Right? Let us do that. Now what is a to the power minus m? A to the power minus m is, there are two ways, a to the power m inverse, or which is same as a inverse to the power m. We have seen this, okay, this is already known. And similarly a to the power minus n is a n inverse, which is also a inverse to the power n. Okay, so we can use any one of them. Let us see. A to the power minus m into a to the power minus n is a m inverse and a to the power n inverse. Now recall, if I have x and y in a monoid and both are in units, then we have seen xy is a monoid and its inverse is y inverse x inverse. Therefore this is the inverse of a to the power n into a to the power m and its inverse. Right? But n and m are positive. We know a to the power n plus a to the power m is a to the power m plus n, which is same as in inverse. But again, by our definition, we know that a to the power inverse is what we denote by a to the power minus n. This is the definition. Right? A to the power minus n by definition is a n inverse or a inverse to the power n. So this object is nothing other than a to the power minus I m plus n. So result is proved. Okay. And the second one is, okay, right, we proved for both negative, right? Now suppose one is positive. Let us assume n is positive, m is greater than m, and that is greater than 0. These are all integers, of course, right? Then I want to know what is a to the power minus m into a to the power n, right? The trick is again the similar thing. A to the power minus m, keep it as it is. Okay, this a to the power n I can write as a to the power m into a to the power n minus m, right? And what is this? This object is nothing other than a to the power m inverse by definition, right? And this is a to the power m into a to the power n minus m. Therefore this is one or identity. Therefore it is a to the power n minus m. So the result is proved if one is negative, one is positive, but then this way. Suppose the other way around, it's exactly the similar thing. Suppose n is less than, okay, m is greater than n and greater than 0. Then let us look at what do I have. I have a to the power m and a to the power minus n. Then you do the same trick. A to the power m minus n into a to the power n into a to the power minus n. Okay, this is a to the power m minus n into a to the power n into a to the power n inverse. So it is a to the power m minus n. Okay, right. And this one you should know why this is true. In both the cases I used a to the power m, assuming m is greater than n, a to the power m is m minus n into a power n. Do you remember? Our general associative law said if a n and if 1 less than or less than n, then this will be a1 to ar into ar plus 1 into an. Whatever we define a1 to ar, a1 to an is I can break it into a1 into ar plus 1 an. So this a to the power m, I can divide the same thing, a m minus 1 n times and a n times. So that's what we wrote. Okay, I hope I covered this. The next one is again something very similar. Remember, we proved if a is in G in a monoid and a to the power m n is a to the power m n, where m and n are non-negative integers. Now we want to extend it. So second thing we want to prove is a to the power m n is a to the power m times n. So again we break it into cases. If m n are greater than or equal to 0, already seen. Okay, suppose m is negative and n is greater than or equal to 0. Let us assume positive, otherwise these things are easy. Okay, because if n equal to 0, then group element to the power 0 by definition is the identity, right? And n is 0, therefore this is a to the power 0, again identity, so it's a true. So we can as well assume they are non-zero. Now let us look at this. Therefore a to the power m, what I am looking at is a to the power minus m to the power n. I want to know whether it is a to the power minus m times n. This is what I want to do, right? Okay, now let's go back. Again you can see we are simply using various definitions. A to the power minus m to the power n by definition is, let us see which is the easy way for me. It is a to the power m inverse and this to the power n, right? A to the power minus m is a to the power m inverse. Okay, good. Now the next thing is, this is called, this is b if you want, b inverse to the power n, where b is a to the power m. Okay, b inverse to the power n by definition is b to the power minus n, right? Therefore it is going to be a to the power m, right, to the power minus n. Okay, what I have got? Yeah, this is not what I want. Okay, let me do this. I just checked it. Let me just check. These things require little time. Okay, let us do that properly. Maybe I will do the other way around. Let us assume but both negative first. A to the power minus m to the power minus n. This by definition is a to the power minus m to the power n and this to the power inverse. You understand that? B to the power minus n is b to the power minus 1 to the power n. Whatever I wanted to use earlier, that's all. Okay? Very good. Then this one, I want to know what it is. Yeah. See. Okay. Let me just do it the other way around. See, this kind of thing, you have to try and get it. If you have good memory, you know which one you want to do. But let us see. My struggling should help you. There is nothing wrong. Okay. So let us assume these are both positive. I want to do. But what is this by definition? A to the power minus 1 to the power m. And this to the power n. Right. Therefore, if I put b equal to a to the power minus 1, this is an element of the monoid. Right. Therefore, this we had already seen for a monoid, b to the power m n, and m n are positive. We have seen it is bm. Therefore, this is going to be a inverse to the power m n. But then this by definition is a to the power minus m n. Right? Because what I have seen, a to the power minus n is same as a, take inverse of a and to the power n. If a is invertible or a unit. Is that clear? Yeah, okay. So we proved it for the case both are positive. Sorry for that goofing, but it's okay. The next one I want to do is if both are negative, that is a to the power minus m, a to the power minus n. Okay. This one what we will do is think of this as a b to the power minus n. Therefore it is b to the power minus 1. Okay. And take its power n and then take its inverse. Right. But notice that in the by the first case, this is a to the power minus mn inverse by case 1. If you call this case 1 by case 1. But this by definition is a to the power mn. Right. Okay. Because remember a to the power minus n by definition is a to the power n inverse for any n. Okay. So this is a group element, its inverse is this. Okay. And this is a to the power minus m times minus n, that is a to the power m. So this also we proved. The next case is a to the power m to the power minus n. Okay. Right. I am looking at all cases. This is a to the power m. Okay. Inverse to the power n. Right. Some this is like call it b to the power minus n is b inverse to the power n, and that's what I'm using. Okay. But we already seen a to the power m inverse a to the power minus m and the whole thing to the power n. By the previous case it is a to the power minus mn. So after struggle various things, I think we have proved all the possible exponents. There is one more. Yeah, there is one more thing. Yeah, remember the third exponent is in a and b are in G, a monoid, and a b are inverses, are units, and a b equal to ba. Then we have seen for any n positive, a b power n is a power n, b power n. So now we want to extend this to for every integer n. Okay, let us assume n is okay. That n is positive. Then a b to the power minus n. I want to know whether it is a to the power minus n, b to the power minus n. Okay, this is what I want to check. So let us start. A b to the power minus n by definition is a b inverse to the power n. Right? Call this as c. C to the power minus n is c inverse to the power n. But I know what is a b inverse. A b inverse is b inverse a inverse to the power n. Alright. Okay. Now these are two elements and n is a natural number and b inverse a inverse are elements of the monoid, and they commute. Remember if a b equal to ba implies b inverse a inverse equal to a inverse b inverse. A inverse and b inverse commute, because what is the inverse of this? Since these two are equal, their inverse are equal. But this is b inverse a inverse and this is a inverse b inverse, so they commute. Is that clear? Therefore since these two commute, and we had already seen we can use this result for n is positive, this is b inverse to the power n and a inverse to the power n. But then what is b inverse to the power n? That is by definition b to the power minus n, a to the power minus n. Yeah. So what you have shown is ab to the power minus n is b to the power minus n, a to the power minus n. Okay. Pause, review, proceed. But ab is same as ba. Therefore, applying the same logic, we are going to get a to the power minus n, b to the power minus n. Therefore, we have proved ab to the power minus n equal to a to the power minus n, b to the power minus n. Okay. I hope I have proved all those things. I hope I proved all the law of exponents. Okay, and that's it. After this, we will define a group and look at examples of groups. Okay. Now we have done all the preliminaries. Now I am ready to define a group, and I will start define a group and stop with that. Okay, and the examples of group we will do next in the next video. So your group by definition is a monoid in which every element is invertible or is a unit. So what does it mean? Let us look at the regular definition. Okay, G is a non-empty set. We don't require that, but we will see that there is a binary operation, G cross to G binary operation. Okay, it has a binary operation. 2, the binary operation is more associative. 3, there is an identity element. What does it mean? You know what it means. And fourth one is for every A in G, there is a B in G. That is, every element is invertible. That is, AB equal to BA equal to 1 or identity. This is what a group is. Now, the first example one should always think about is integers under addition. Okay, right. And also I can think of non-zero. Let's look at the rational numbers, non-zero rationals under multiplication. Okay, that means the group operation, if two rational numbers are given, these are ordinary product of rational numbers. And one is the usual one. And we know it has all the properties. If R is P by Q in the lowest terms, then R inverse is Q by P. Okay, these are the two things. But here, these examples are very somewhat, okay, yeah, special, because in this you can see the binary operation is commutative here in these examples. But in general for group, we are not assuming commutativity. We are assuming only associativity and then existence of identity and existence of inverse for all these elements. So we will stop, and the real thing which you are expecting of groups we are defined. In the next lecture we will look at a few more examples and some other properties. Almost all the properties you need are already established. Okay, life will be much easier for us, then we can focus on the other things. Okay, stay tuned, and again my word of warning, don't give up. Okay, just watch again, and at least few of the points make sure that you understand 100%. Okay, and slowly when time permits you reflect upon the others which you have not understood properly. Okay, wish you a good time. We will meet again.